Hi everyone, in this video I'd like to introduce this process of actually long division algorithm for P-adic integers. So in this video I'm not going to go through what a P-adic numbers are, and then I assume you already know what a P-adic number is, and I don't think this algorithm is any importance to number theory who studies P-adic integers and so on. So I don't think many people have seen it. Actually, I've never seen it, so I invented it. I was preparing a talk for those people who've never seen a P-adic integer. I thought this is a fun thing to show. So let me start. So I'll be very brief in this video in explaining things, because I assume that you already know what P-adic numbers are, and you know, you have the basic. It's something that I assume that you have never seen this before. So let's review division and decimal expansion first. So I'm dividing 1 by 3, and this is one algorithm I learned at school in the early stage of my education. So I first look at 1 and try to divide it 3. It's too small, so you go to next digit, which is equivalent to multiplying 10 in there. That's going to be justified in this area. So then the integer multiple of positive integer multiple of 3 fit in. There's 3 goes there. That's the maximum that is less than or equal to 10. And you subtract off and multiply by 10, which is the same as putting 0 there. And you repeat this process again and again. And this number here is supposed to be the decimal expansion or decimal approximation of 1 divided by 3. So if you think about it, it's the same thing as this one. 1 over 3 is expanded in terms of decimal expansion, whose algebraic expression maybe is like this. So geared toward to explaining this algorithm, this is what we're going to do. We actually multiply 3 to the other side. So it's written on the left side. It's looked like this. And figuring out that this digit is multiplying 10 both sides. So I multiply 10 both sides. That becomes a 10. That becomes 10. It's multiplied inside the parentheses. So it looks like this. 10, it decreases the power in the denominator. So this just becomes a number. So what we do, we figure out the largest integer here. That kind of knocks down this 10. So that's this part right here, filling in. So C1 is going to be 3. So that's going to be 1 there. So I'm showing here 3 times 3. So that's 10. So if you subtract that part, it's going to be just 1, which is what you see over here. And also written here, once you subtract off, you have 1 here, and you're still looking at 3 times some decimal expansion that looks a lot like what you started before. So you start all over again from this process and multiply 10, which is this stage here, then figure out the integer multiple and subtract off. Alright, I was preparing a little colloquium talk for the P-adic numbers. That's why it said it's a part of that slide I extracted from it, and that's why I say back to P-adic. But what we're going to do is that we're going to divide 1 by 3 in 5 adic numbers, so in the ZP. So let's make an analogous statement we did for the decimal expansion. For example, this is what we're looking for in the P-adic. 3 times what number in the P-adic integer is going to be 1. So that's exactly 1 divided by 3. So how to find this A0 is the modulo P calculation. So first you choose 2, because 3 times 2 is it's 1 mod P, which P here is 5. So that's why we choose this one. Then we multiply this, that you get 6 out of it. So and subtract from both sides. So that's why you see 1 minus 6. And rest of the part still have 3 multiplied to it. So we get negative 5. Notice that this part is going to be always a multiple of 5, because that's how we choose these numbers. You subtract it to have the same value in the modulo 5. So we have 5 here, and everywhere we have P multiplied. So that's how you get to the next level and look exactly like that. You just divide both sides by 5. But before, in the decimal extension, we multiply by 10, but here we're actually dividing both sides by P. Here is 5, and then we get to this position exactly. So that's why you see the next line. I'm going to kill the 1 copy of P everywhere. So that gives you A1 and A2 P to the first, and if you kill that, it's a negative 1. So we're back to this place where it looks just like that. Actually calculating this process, the coefficients of this p-adic integer, is completely explained in something called the Hensel's lemma. But Hensel's lemma is less efficient than this one. This algorithm really uses one digit at a time. It's in the basic version of the Hensel's lemma requires actually a larger number to deal with than what this calculation is showing. So let me proceed. So here's the next part. We're looking at -1. That's the same as a 4 mod p. P here is 5. So what should be multiplied here to match that modulo 4? That was 3. So it's a 9. So it's a 4 mod 5. So we're going to choose that such that when you subtract this part off from both sides, you end up at a multiple of 5 again. So when you do that, it's a 9 minus -9 on the one side, so it's -10 on the right hand side. So that is again a multiple of 5, so we divide both sides and you get it. So you get to this stage. So a2 is here and a3 and knock down 1 power, and this, if you cancel a factor of 5, and then you end up at -2. And from here we repeat this process again and again. So we're going to put this algorithm into a decimal expansion long division process. Let me first put it in this way. 1 is we're dividing 1 by 3. Same thing with the principle of choosing this number to matching these congruence class modulo 5. So what should I multiply here so that this congruence modulo class is the same? That one goes here is a 0 to 4 because we're doing 5-adic. So 3 times 2 is a 6. That's 1 mod 5. So that's why we chose that. So we subtract. So I subtracted as a -5. This is supposed to be multiple of 5. The next thing we do is, instead of putting a 0, that's how you do it in a 10 decimal expansion, instead we have to knock out a copy of 5 here. So if you divide that one by 5, that's going to be -1. That's why you see number over here. I put a little separator so that you can separate and see what the procedure is. -5 divided by 5 is -1. So we start all over again, start from putting in the right number here so that this one get the same congruence class. Remember that one's 4 modulo 5, so we have to put something here. So here if you put the 3 times 3, it's a 9. So 3 times 3, it's 9. So if you subtract that, it's going to be -10. That's multiple of 5 again. So here I put -10. So we got that part. It's kind of remainder. Then you have to knock out 5 again. So that's going to be -2. So I wrote it here. So we start all over again with this -2. So put some number to match the congruence class, which is 1. 3 times 3 goes to 3. If you subtract the -5, a multiple of 5. So multiple of 5 and -5s, and you knock out 5, so -1. Then of course we already did the -1 here, so what goes up there is exactly the same as that one. So we start from 3, and it's kind of easy to see because our algorithm just perfectly rely on this remainder part that we're kind of looking at. And as we do that, so you can see from here it repeats 3 1 3 1 3 1, and from this it's kind of easy to explain why all the global rational numbers are periodic in p-adic expansion. So p-adic expansion of 1 over 3 is starting from the a0 part is a 2 3 1 3 1 3. It repeats over and over. So that's our p-adic expansion over 1/3. So in the next part of the video, I did this long division of 1 divided by 33 in the 5-adic integers again, but this time I'm not going to bore you going through each process. If you're inclined to do that, maybe you will do it yourself, and I'm just going to show you in a second that my answer to the long division, adding just a few facts about the process. So here's my answer. I put 1 and 33 and went through each process and over, and we got this string of numbers in between 0 and 4. And that's going to be the p-adic expansion. You might have noticed that when you did it and through my process, this number is actually what you're dealing with. -13, -29, -19, negative 17, and negative 8. And those numbers what you're dealing with. And you might have noticed that that's always less than 33, and that's always true. Then you can imagine if you start with some number that's bigger than 33, this process will knock down by subtracting it eventually smaller than 33. You will get to this range anyway, eventually. So let me explain briefly why this is negative less than negative 33, and that explanation I think is quite general, so you will expect that kind of smaller size when you do these long division for decimal numbers. So I inductively prove that if I call that number, this is not an. I'm sorry, I should have used a different notation. An is not these coefficient of p-adic, this remainder I was thinking. So I put an there. So if I have an that is in between, it seems like less than in between 0 and negative 33. So we show an plus 1 through that process, still in between 0 and negative 33, and that's what we have to show. So the process is that you find this appropriate multiple of 33 and you subtract from it here an minus 33k and divide it by 5, and that's how you get to the next number, an plus 1. So I wrote down and do the same operation to this both side, and that's what you get. You can see this is always less than 0 because k is in between 0 and 4. I don't think I pasted this all apart, so but I moved up a little bit. So it now shows that my expectation is less than 33. So what we have here is less than 0. That's still untrue. And that part here, since k is between 0 and 4, k plus 1 will vary from 1 and 5. So if you divide that by 5, you definitely get this part here less than 1. So that proves this is still true for next level an plus 1. So that's it. Thanks for listening.